So shall we start? Good morning. Where do you switch this thing off? Ah, yeah. No. So I forgot at the very. I should have said this at the very beginning, and one of you reminded me that I should mention some books, and maybe with a few comments. There are also other books, but those are the books that I've looked at when preparing these lectures. And of course, there's much more material in them than I could cover even in a whole semester. So let me just say a few words about them. This is also a classical book, but it's a little bit out of date because it was written in the 60s. So, for example, this doesn't have non-abelian gauge theories in it, but I find the first few chapters of it still very useful. This is rather encyclopedic. In this book, if you're looking for a topic, any topic, you're most likely to find it here. The same is true of Weinberg's two books, which have appeared only very recently. They're also there's a lot of material in them. And it's also a more modern presentation. Weinberg also starts the course on quantum field theory by first discussing representations of the Poincaré group, which is also what I did. But there's a lot more material in here, also modern stuff. For example, also non-perturbative methods in quantum field theory. And there are very, very many applications in here. This is the book which I like best from a pedagogical point of view. It's very well written. It's not very comprehensive, but it still covers a lot of material. And if I were to choose, if I had to follow one of these books had to choose one of these books for one semester course, I think I might follow this one. Then there's also Feldman's book. This book is this has a different point of view. I told you that in quantum field theory there are various approaches because as a mathematical theory, this theory is not really a theory, and either you can approach it in a more axiomatic fashion, or you can just approach it as some kind of prescription that tells you how to calculate scattering amplitudes and other quantities of interest in quantum field theory. And this is the point of view adopted here. And if you want to learn quickly, get quickly to the real meat of quantum field theory, in the sense that if you want to learn quickly about how to calculate scattering amplitudes and so on, then this is very well described in here. And then, of course, there are the two classic books of Bjerke and Drell that I suppose I'm sure that everyone here has looked at volume 1, Relativistic Quantum Mechanics. That's where you can learn about the Dirac equation. The second volume is much more formal, and it treats quantum field theory the way I've been doing it. So here, in this one, they also derive Feynman rules, but this is done in a much more heuristic way, whereas the systematic derivations are then in this volume. But they themselves express the point of view that there's a lot of formalism here, and they're not so sure about whether this formalism in the end is really so essential. They say that the real physics, in some sense, is already given here, and is already contained in the heuristic derivations, which of course contain the great insights of great physicists like Feynman and others. So, today we move on to interactions, and as I said, to make this course a little bit different from the standard quantum field theory course, then I will also spend some time on supersymmetry. Well, so far we've been dealing with scalar fields, with free fields, and we've been looking at spin 0, there's the scalar field of spin 1/2. And if I had more time, I would have now discussed the spin 1 field, the photon field, and how to quantize it. That's still a little more complicated because you now have to take into account the gauge invariance. But let us stop here because essentially what you get is again the same statement, that this system describes an infinite collection of harmonic oscillators, and the only technical complication is that you now have polarization states, like already for the spin 1/2 field. Now these three fields are described by linear equations of motion. And because the equations are linear, we can solve them both as classical equations, but as I've shown you, you can also convert these classical fields into quantum operators, and you can also solve the equations of motion of the quantum operators. This is simply done by taking the Fourier expansion and then converting the Fourier amplitudes into creation and annihilation operators. Now this is all very nice, but of course it's not really a very interesting world, because if you prepare any state, an n-particle state in quantum field theory, you will just stay there forever. If you put n particles you prepare a state with n particles of definite momenta, then this state will persist forever. So at some point one wants to move on to interacting fields. And that means going from linear equations of motion to nonlinear equations of motion. Well, first of all, at the classical level, and this is what I will spend most of today's lecture on. But then you will also have to worry about how to quantize such theories when you have nonlinear terms in the equations of motion. So let me give you some examples how you might do this. And these examples are already oriented a little bit towards physical applications. Well, we started out with the Klein-Gordon equation, which was based on a Lagrangian, which we can write like this: 1/2 m squared phi squared. So this is the Lagrangian that upon variation gives rise to the Klein-Gordon equation. And we can now modify this by adding higher order terms. For example, we can add a term here, 1/4 times lambda phi to the 4th. The equations of motion you get then are as follows. We have a box plus m squared phi of x is equal to minus lambda phi cubed of x. This theory is called phi to the 4th theory. It's been given this special name because this is, if you like, this very simple model of an interacting quantum field theory, and this is why it has been studied a lot, and that's why it has been given a special name. So what does this, what do we see here? We have the free part of the Lagrangian, and now here we have something, well, this is a 4th order monomial, and this we can schematically describe by writing a vertex with 4 lines coming into it. This is already with a view towards a Feynman diagram expansion later on. When you do perturbation theory, then you will have propagators, and then you will have interactions where 2 particles can come in and 2 others come out, or whether 1 particle comes in and decays into 3 others, and this will be this will come from this term. So at the moment, I don't want to formalize this any further, but I think it should be obvious that you have 4 fields, that then it's plausible that we will get an interaction like this. Now, of course, here you can add many more. You could now start adding 5 to the 6th, 5 to the 5th, as much as you like. Well, as it turns out, this is, if you add 5 to the 6th and higher order terms, this is not so interesting in a sense, because it turns out that there's an extra requirement imposed on these theories, which is called renormalizability. And renormalizability is, this model is only renormalizable with this kind of interaction. If you have higher order interactions, it will no longer be renormalizable. And that's why so much effort has been concentrated on this theory. Well, there's been a lot of work on it in perturbative analysis, but I should also say at this point that we nowadays believe that this theory, with this term, does not exist as a quantum field theory. If you look at it, it exists order by order in perturbation theory, but it's now generally believed that this theory by itself is not a... If you try to think of it or define it as a quantum field theory at all orders, it's believed not to exist, but nonetheless it's a useful model. And of course you also know that this can, if it's not viable by itself, it can occur as part of some bigger Lagrangian. For example, the standard model, there you also have scalar fields, and not just one. And of course you need such terms for these, for example, in the Higgs potential, then you will need such terms. So that's the simplest example. Another example is QED. Here we write L, I'll give the factors right. We have psi bar plus I gamma mu d mu minus m plus E times gamma mu a mu times psi minus a quarter f mu nu. Now what is this? This is the free Dirac theory that we discussed yesterday. So this is free, this gives the free Dirac equation. This is something I did not discuss, but you know what it is, I suppose. This is the Lagrangian for the photon. It's a free Lagrangian where we define, of course, f mu nu is equal to d mu a mu minus d mu a mu, and a mu is the photon field. And this here, and this is a, so this up to here, multiplied by psi, this is quadratic. This will give rise to linear equations. This by itself is also quadratic, because f mu nu for the photon field is linear. So this by itself would also give rise to a linear equation. That would be the spin 1 case I haven't discussed. And now here we have a term which is of third order in the field. And this will induce an interaction which looks like this. So again, we draw a vertex, and we have a line coming into it. So we have two fermions running into this vertex, or out of it. Well, of course, you know that depends on the details, of course, whether the electrons or positons meeting at these vertices. So, for example, you have electrons moving in, coming out, and here, so an electron here, and here there's a photon denoted by gamma. And the equations of motion you get from this are the following. I gamma mu d mu plus E gamma mu a mu minus m psi equals 0. And if you vary the equation with respect, vary this Lagrangian with respect to mu, you will find that d mu nu, f mu nu, is equal to plus, well, E psi bar gamma mu psi, and this I call a current. This is the electric current, and it's conserved. So what you have here is Maxwell's equations with a source term on the right-hand side, which is just the electric current. And here, in turn, you have the equation of motion for the Dirac field in the background of this photon field. So taken now in undergraduate electrodynamics, the way you solve these equations is just to look at this equation and you give some source. But here the equations are more complicated because the source itself, or the field that enters the source itself is determined by an equation that again contains this mu. So this is now a coupled system of equations which is more difficult to solve. So that's a second example. Now I have another example in closer to, so it's a bit old-fashioned, but this is a description of pion-nucleon interactions. It's a sort of phenomenological description. Well, in the old days, people were studying scattering of protons and neutrons. And well, here comes a concept that is very important. The fact that we can restrict the form of these interactions by imposing certain symmetries. And the symmetry one imposes here is isospin symmetry. And isospin, as you know, means that we have a sort of internal spin distinguishing the proton and the neutron. We think of the proton and the neutron as being, one kind of object, but with different orientations in this isospin space. And this you describe by introducing an isospinner. And an isospinner, here in this example, is an object where we combine the spinner or fermion field describing the proton with that of the neutron. So we have here a spinner that has the Dirac indices, and on top of this has an index A that assumes two values. So this is a Dirac index, and this is an isospin index. And this is now a spinner with 8 components, where the upper 4 components refer to the proton, and the lower components refer to the neutron. And this index A refers to P and N, or N. So this is now a new kind of object, and this thing we want to couple to a pion field. So pions, what are pions? They're an isospin triplet. So we introduce 3 scalar fields, phi A, phi 1, phi 2, phi 3. And these will be related to the pion as follows, while pi 0 will be put equal to phi 3 and pi plus minus. These are 2 complex fields which we can manufacture out of 2 real fields. So we define phi 1 plus pi phi 2 or minus. So here you can again see that a real scalar field corresponds to an uncharged particle. A complex scalar field describes a charged particle. So, in order to, we can again write down a Lagrangian, and of course it will contain these pieces corresponding to the 3 Lagrangians. So this I will no longer write down because it's the same as before. But we now want to write an interaction that respects this isospin symmetry, isospin SU2, I should say, somewhere, SU2 isospin symmetry. And in order to do this, we must couple these indices somehow, and we have to use Pauli matrices for that. Now normally this designate Pauli matrices with the letter sigma, but here we do it with the letter tau just to make clear that this acts on isospin indices. So the tau AB are just the Pauli matrices. And now given this Pauli matrix, we can write down interaction Lagrangians. So L will be L3 for these fields, which is the same as before, plus, and now I can write something like, well, there's a coupling constant, pion-nucleon coupling constant, and then I write something like psi bar, gamma 5, tau A, psi times phi A. So what is this? Well, here I've written out if I write out the isospin indices, it's like this. And then there are also Dirac indices. And here I've inserted a gamma 5 matrix because the pions are pseudo-scalars. So this is again scalar. So this, you see, is now a vertex. It looks like this. So here we have this proton or neutron coming in, and then here we have a vertex where it interacts with this other particle, and then we have the pions coming out here. Well, this is of course a phenomenological ansatz. It's not a fundamental theory. It's a parametrization which we can try to describe pion-nucleon interactions. Of course, from here, then we would have to go on, calculate cross sections and so on, compare with the experiment, and check whether this ansatz makes good predictions. Now, of course, this is not the only possibility. There are many others. For example, I could now add a term like this with another coupling constant, where I now insert a gamma mu matrix. Tau A, AB, psi B, d mu phi A. So that would be another kind of vertex, and so on. Now it seems at this point that the possibilities are virtually unlimited, because especially if I allow myself higher order interactions. Now again, the requirement of renormalizability sort of eliminates many of these possibilities. So this one is okay, but this one is non-renormalizable. So if you want to treat it really seriously, then you cannot regard this as part of a fundamental Lagrangian. Anyway, we nowadays know that this is only an effective description, whereas the underlying theory is QCD. And if we really understand QCD one day, we should be able to derive these sort of effective theories out of the more fundamental theory. So this is Lagrangian is invariant under isospin transformations, which I don't want to write down. So, as I said, here we have 3 examples where we can now ask ourselves the question: what are the possibilities? Are there any general requirements that we have to pay attention to when writing down such interactions? Now, I come back to my first lecture because I stated that there are certain principles of quantum field theory that must not only be obeyed by free fields but also by interacting fields. And these principles restrict the possible form of the interactions. Possible interaction term, interaction terms are restricted or constrained by some general principles. Principles of quantum field theory. Let me recall what they are. Maybe first of all, Poincaré invariance. Now that's pretty easy to check, because if you set up the formalism using 4 vectors, relativistic notation, then Poincaré invariance or relativistic invariance is simply ensured if you just contract indices in the right way and we don't single out spatial and time indices, and then this is manifestly Poincaré invariant. So all of these interactions obey this principle. Well, the second requirement we'll impose is that of hermeticity or unitarity. Or hermeticity. Now, what is that? That is whatever Lagrangian we write down, call it L, we have to impose the requirement that it be a real quantity. So, at the classical level, we have to impose this requirement. Now, it's obviously true here if you choose this coupling constant to be real. So this requirement would disallow coupling constants which have an imaginary part. Now, what is this? Well, if I have a real Lagrangian, it means that we will get a Hermitian Hamiltonian operator upon quantization. Now, this is the operator that governs time evolution. So, time evolution, the time evolution operator is u equals e to the I ht, and with this requirement, the time evolution operator will be unitary. And unitarity ensures that probability is conserved. If the Hamiltonian wasn't Hermitian, then we would have a real part here, and that would mean that something disappears. Sometimes this is used for the effective description of decays in quantum mechanics, that people write a Hamiltonian, they add a small imaginary part. Now, in ordinary quantum mechanics, of course, this also ensures that eigenvalues are real. But here, there's also a connection with the unitarity of the Hilbert space, and basically the connection is this. So then I had said that we insist on local interactions or locality. So that rules out terms like, for example, terms like, if I write an interacting Lagrangian, phi squared x, f of x, y, phi squared y, dx, dy in the action. So this kind of term would be disallowed. So, because such terms would then give rise to propagation at speeds greater than that of light, and we cannot expect that such a theory, if we add such a term to the model, that when at the end of the day we calculate the commutation relations of the field operators, we cannot expect them to commute at space-like distances. Now, so these are very general requirements, and I told you already last time that with the apparatus of quantum field theory, we then can derive some very general consequences, and one of them is the spin statistics theorem. So in fact, there's a branch of quantum field theory called axiomatic quantum field theory, and that's their the main contribution, really, their claim to immortality, as it were, is the statement that these two general theorems which we can prove. One is the spin statistics theorem. So this one can prove, you have to formalize this a little more, but can prove that you have a spin statistics theorem, meaning that half-integer spin fields are always fermions, and integer spin fields are always bosons. So it's one. And the other one is the so-called CPT theorem, according to which we have three discrete transformations, symmetry transformations in quantum field theory, namely time reversal, parity, it's clear what it does, and charge conjugation, which exchanges particles and antiparticles. And this theorem states that the combined operation, a CPT, is an invariance of the theory. And so you're not allowed, I mean, you cannot, if you use this as an input in the theory, you will not be able to obtain a contradiction with the CPT theorem. So as far as I understand, there are tests of this CPT theorem, for example here at CERN, and it would be quite a revolution if someone discovered that CPT was not a symmetry, because it would mean that this whole framework would collapse. So it better be a symmetry. So now you also know that in quantum field, in nature, it seems like CPT is an invariance of nature, for all we know, but it doesn't mean that these invariances are separately symmetries of the theory. So, for example, you know that, but C, P, and T need not be symmetries separately. So we have violation of P, violation of parity in weak interactions, discovered in the 50s, and we also have CP violation, which is by this theorem equivalent to violation of time reversal invariance. The KK bar system. Well, there's also strong CP violation, but so the thing then is you can write down Lagrangians that separate these invariants, or do not respect these invariances separately, but whatever you do with these requirements, at the end of the day, this will be a symmetry of your theory. Now, this is already gives you some hint as to how to construct theories, but there's of course more. Now, so we have these requirements, but now very important extra input in the construction of quantum field theories, the requirement or the existence of symmetries. Now, what symmetries do I mean here? Well, here we have, of course, Poincaré invariance. That's taken for granted. We'll no longer talk about this. Then we also have these discrete symmetries. But on top of this, now we have further symmetries, meaning continuous symmetries, not discrete, of the same type, or generalizing the isospin invariance in this pion-nucleon system. Now, these symmetries come in two varieties, namely, we have symmetries so-called global, or a better word is rigid symmetries, or local. Now, global symmetry is a symmetry like isospin symmetry that acts independently of the space-time point. So, for example, this model is rigidly symmetric with respect to isospin SU2 symmetry. A local symmetry, on the other hand, is what's called a gauge symmetry, also called gauge symmetry, is a symmetry which depends on where you are in space-time. So here, if you have a rotation parameter, a rotation parameter like an angle of a rotation in isospin space is independent, alpha is independent of x, Minkowski space. And here the parameter is alpha depends on the space-time point. So we have these two symmetries. And both of them seem to play a role, whereas in the old days, however, it was more the rigid symmetries that seemed to play a role, like isospin symmetry or Gell-Mann's SU3 flavor symmetry for the quarks. It seems now more and more that in some sense, more important symmetries are the local symmetries, because the standard model is based on Yang-Mills type theory, and it means it has a local symmetry with respect to a certain group, SU3 cross SU2 cross U1. So here I will show in a moment, will be led to so-called Yang-Mills theories, which are basic for understanding of nature. But before I go there, I want to state a very general theorem, which is the following. It's called Noether's theorem, and this theorem states the following. Noether's theorem it states that for every continuous rigid symmetry there exists a conserved current let's call it J mu of x. And conserved means that d mu, J mu equals 0, and with appropriate boundary conditions, meaning in practice that the fields should fall off sufficiently fast at infinity, boundary conditions, a conserved charge, Q, and this charge is constructed by taking the zeros component, the charge density of the current, and integrating it over some spatial hypersurface. You can integrate it over a flat three-dimensional space, but you can also wiggle it a little bit. That doesn't matter. Now, that is conserved because if you hit this with d by dt, you take the time derivative inside, then you use this equation, and then you get a spatial divergence of the current, the space current, and then you use Stokes' theorem to convert this into an integral over hypersurface, the boundary. And then if you assume, and this is where the boundary conditions come in, that the fields drop off at infinity, then you'll get 0. So this theorem is rather easy to prove and also quite general proof. So let's assume that L, some Lagrangian, depending on some set of fields which are labeled by phi of A, can also be spinor fields. It's not the same label as here. It's just any label. And let's assume that it just depends on these fields and their first derivatives. But of course, you could also generalize it to look at more general situation. So let this be invariant under some transformation. Delta phi of A. Well, I said it's some transformation. I don't even have to specify what it is at this moment. So that means that if I vary these fields in here, then delta L will be 0. This is the assumption that it's invariant. This is the assumption. Now how do we calculate this? We calculate dL by d phi A times delta phi A plus, and then we also have to vary the derivatives, delta d mu phi a, delta d mu phi a. So that's the variation. First of all, we use that the variation vanishes. This is invariant. And then we evaluate the variation using this, whatever this transformation is. And then we rewrite this a little bit. And we rewrite it as delta phi a, dl d phi a, minus. So now add a term and subtract a term in the following. So this term I add or subtract. I have to compensate for it. And if I add this term, then this to this term combines into a total derivative, which can be written like this. D mu phi a times delta phi a. And now if we look at this expression, we see that these are just the Euler-Lagrange equations. So Euler-Lagrange equations tell us that this is equal to 0. So this is equal to 0. And now here we have the statement that the divergence of something is equal to 0. So this something here is essentially the symmetry current. So this defines the symmetry current times this transformation parameter, alpha, which I haven't written out here, but there's always a parameter which parameterizes this transformation. Now, here the rigid plays a certain role, because if it's independent of x, then I can just pull out this transformation parameter and I get the statement that this is invariant. So, let's see how it works for example for QED. Well, this Lagrangian is very invariant under gauge transformations, in particular under. Well, let's forget about this term for the moment. Let's just look at these two terms. Then this is invariant under a phase rotation of this field, and as long as this phase rotation parameter alpha does not depend on x, we can just pull it through this derivative. When it depends on x, this is of course where we need this extra gauge field. So it's invariant under delta psi. Let's write this as plus I alpha psi and then we get, we just look at this expression, we get delta d mu psi times delta psi, so this is I alpha psi. And now when you do this variation with respect to this term d mu psi, so take the derivative, then you get psi bar I gamma mu. And this is multiplied by, so it's I psi bar gamma mu, and this is multiplied by this thing. So here we have the parameter, which we can forget about, times psi bar gamma mu psi. And this, up to a factor, which we can always include, is precisely the conserved current which appears here. So I've recovered the well-known statement that in this theory we have a conserved current. And this was just to illustrate that this, how this the proof of this statement works in the case of the Dirac-Lagrangian, but it's a very general statement. It's also true under much more general circumstances. Now, the next step, I said these are rigid symmetries, and we now want to see what happens if we introduce local symmetries. So how do you make the transition from rigid to local? That means that we take alpha now to allow for an x dependence. Now, then we can still use this argument over there. We can still go through the same argument, But then we will find that if we make this with this substitution, that delta L is equal to d mu alpha j mu. Oh, this previously there was just alpha times. But now we get an extra term, namely plus d mu alpha times j mu. So what is this? This is precisely the phenomenon that when you take this Lagrangian, take a transformation parameter which does not depend on space-time, then this thing by itself is invariant. Now, if I allow for an x-dependence of this transformation parameter, I will pick up an extra contribution because now the d mu also acts on the transformation parameter, and this is precisely this term. So, in order to make the Lagrangian invariant again, I need something to cancel this term. So to cancel extra term, we must introduce a gauge field A mu such that the variation of this delta A mu is proportional to d mu alpha. And furthermore, we must add to the Lagrangian an extra term of the following type, this plus or minus j mu of x times A mu of x. Now, with this substitution, we've started from a series that has a rigid symmetry, like phase rotations in the Dirac theory, or this could also be applied to this isospin invariant Lagrangian, that we have rigid SU2 transformations. We now want to promote them to local transformations, and according to this argument, then there's no choice, if we insist on the invariance of the Lagrangian, there's no choice but to add an extra field to the theory which transforms in this way. Well, this may only work to a given order, so there may be extra terms here. In electrodynamics, of course, this is it, but if you go to the non-abelian gauge series, there will be a few more extra terms here. So, at this point, you've cancelled this term, but then there may be new terms in principle. So let me write dot, dot, dot. And of course, then you will have to check what else you have to add in order to make this invariant. So this thing is called Noether coupling, in honor of Mrs. Noether. And I'm telling you this because this is a mechanism which works very, very generally. It works for QED, and this interaction term is precisely this Noether coupling. It also works for non-abelian gauge series, as I will show in a moment. And it also works for gravity, in some sense. Because if you have a spin 2 field, then you would, if you couple matter to gravity, then the current, there's also a current, and that current is associated with the Poincaré group, and the conserved current there is the energy momentum tensor. So the energy momentum tensor is exactly on the same basis as the electric current. It's a conserved current. It gives rise to conserved quantities, the momenta. And furthermore, if I make this translation invariance local, I get general coordinate transformations, and then I couple this conserved quantity, namely the energy momentum tensor, well, to a gauge field, and that gauge field then is the graviton. So this principle, which looks almost trivial in this situation, which we are very familiar with, also works in more complicated situations. And in the case of gravity, of course, this is not all, but you will have to add an infinite number of terms here. Whereas in the abelian case, this is already enough. And if we do QCD, then we have to add two more terms, and that's it. So let me say a few words also about Young-Mills theories. This is the basis for the Standard Model. And the point to remember here, or the point I want to emphasize here, is that the nice thing about the symmetries is that they sort of fix this kind of interactions. So for example, in QED, if you insist or impose this symmetry requirement, you are forced to introduce this term and no other term. And the same is true for non-abelian gauge theories or Young-Mills theories. So let me just briefly summarize what happens there. We know gauge theories. Well, in the case of QED, we just had phase transformations, where you transform the spin field by a phase factor, which may depend on x. Now these transformations form a group. It's called U1. So the group G is U1. And non-abelian gauge theories tell you how to generalize this situation, or this kind of this situation, to transformations where the group is non-abelian. So QCD, etc., or Young-Mills. Start from non-abelian group G, like SU2 in this example, or SU3, or SU5, or whatever. Now all these groups are so-called Lie groups. Lie groups very generally means that you can analyze the group by staying close to the unit element. You do just infinitesimal transformations, and then you already know almost everything about the group. There are also other groups which are not Lie groups, but they don't seem to be of such importance in physics. So this means that every transformation in this group can be written in the following way, as e to the a omega a of x times ta, where now this is a set of parameters. These things are called generators, and then we choose them to be Hermitian. So this is unitary generators for a running from 1 to whatever the dimension of the group is. So for SU2, we have 3 generators, the Pauli matrices, for example. For SU3, we would have 8 generators, the Gelman matrices, for example. And for these, you have certain commutation relations, call them TA with TB, is equal to FABC, TC. So this is analogous to the angular momentum commutation relations. In the case of SU2, here you just have the epsilon symbol, and it's really the rotation group. And these things are called structure constants. Well, then you introduce a gauge field, A mu of x. Now this is no longer just a number or 4 numbers, but it's a matrix, and it's defined by expanding it as follows. Every matrix in this algebra, which is called the associated Lie algebra to this group, can be written like this. And then we have a generalization of this field strength of the abelian theory, which is as follows. F mu nu A is now d mu A nu A minus D nu A nu A plus or minus some coupling constant which I set equal to 1 times A mu B A mu C. And then this object again will transform in a nice way, as one says covariantly, and these extra terms here are needed in order to get this covariant transformation law. And given, so this is the non-abelian field strength. And now the invariant Lagrangian here is simply a generalization of the Lagrangian of Maxwell theory. And I take 1/4 F mu nu A, F mu nu A. And if I write it out, I have 1/4 d mu A nu minus d mu A mu A squared. So that's the term we have also for the photon, but there are more of these terms, as many as the corresponding to the dimension of the group. But now we get extra terms, because here we have this quadratic contribution, and then we get minus FABC d mu A nu A nu B A nu C. And if we square this term, we get FABC minus 1/4 FABC FADE A nu B A nu C A nu D A nu E. So this is like the Lagrangian of Maxwell theory. So this is like Maxwell, a photon. But now the symmetry has forced us to introduce these extra couplings. And what is this? This is a coupling of sorry. Oops. This is a coupling of three fields, which, with the notation which I introduced at the beginning, corresponds to a vertex like this, with the three fields coming in. So this is the 3-gluon vertex, if you like. And here we have another vertex with 4 fields coming in. And this is the 4-gluon vertex. So the lesson here is that by imposing symmetries, in particular by imposing local symmetries, I can restrict the form of the possible interactions in a very strong way. And this is, as we now know, this is really the right way to construct the correct theory. You see, this was the way things were done in the old days, meaning in the 60s, when people didn't know about Yang-Mills theories, and not many people knew about them anyway. So you just made these sort of phenomenological Ansätze, and you really didn't know where to stop here. And then you tried to fit all these parameters to whatever you were measuring. But here the symmetry requirement wasn't very strong. Insisting on this on local symmetries, you get much stronger restrictions. And in the case of Yang-Mills theories, you're forced, there's no way to avoid introducing these interactions. And that's really the reason why Yang-Mills theories are much harder to quantize than scalar field theories. Because unlike the scalar free field or Dirac free field, here I cannot start with a free field, because I have these terms right from the start if I insist on the symmetries. Well, as you know then, this is almost enough to construct the standard model, because now what we would need in addition to this is, of course, we would have to couple this to the fermion fields. We have to say what are the fermion fields. But then you also have covariant derivatives. And these covariant derivatives, again, fix uniquely the interaction, say, between quarks and gluons. They are predicted by the symmetry here. So in some sense, all you have to do now is you have to pick the right gauge group. Of course, there was a lot of debate about this some 25 years ago or so. But now we know that the right group seems to be G SU3 Kala cross SU2 weak cross U1 hypercharged. So this seems to be the right nature, the group that nature seems to have chosen, although we're not yet sure whether this cannot be embedded in yet bigger group, say for example SU5. So this is not E6. So this is not yet decided, but the important point here is that simply choosing the symmetry or looking at nature, processes in nature, we can immediately write down the Lagrangian and we can immediately fix the interactions. Now there's one requirement which I haven't mentioned, which I have mentioned, but I haven't explained. It's that of renormalizability. Now that's something where that is an extra requirement, because here, for example, nothing, just looking at the symmetries, nothing would prevent me from introducing, say, a term like this, but squared, or the third power. And so I would still have infinitely many terms. Now it's this requirement of renormalizability, which I will try to explain tomorrow, at least in principle, which forces the number of possibilities even to less than the symmetry by itself. Okay, so I'll stop here. Tomorrow I'll tell you a little bit about yet another symmetry that has become important recently, namely supersymmetry. Maybe it's just around the corner. I hear rumors about events at lab, and maybe you see this stuff within the next year or so. So I think it's appropriate to devote some time to supersymmetry, and this is what we will do tomorrow. Thank you.